Welcome to part 2 of our Introduction to Energy video. In the first video, we focused on definitions such as thermodynamics, which is our main focus for this unit, which is the study of heat changes, and then also the idea of kinetic energy versus potential energy, because it's that conversion between the energy stored in chemical bonds to the energy of movement of the chemical that really allows us to understand what's happening in terms of heat in a chemical reaction. So what we want to have a better understanding of in this video is how can we look at how that heat is changing to determine what's going on with our sample. And all of that kind of links into this word right here, because it's very hard for us to understand that a chemical is moving when we can't see it. But trust me, they are moving. Those particles are in constant motion. And so what we can do is we can use temperature to help us understand how fast or slow the particles are moving in a sample. Because when you guys think temperature, you just think of something's hot or something's cold, but that's really not what temperature is. Temperature is a measure of the random motions of the components of a substance. What does that mean? That basically means that temperature tells us how fast or slow a substance is moving. And the relationship between temperature and speed of movement is that the higher your temperature is, the faster your particles are moving. So if I'm comparing water that's 20 degrees Celsius to water that's 100 degrees Celsius, the particles in my 100 degrees Celsius water are moving faster than the particles in my 20 degrees Celsius water. And it's just like real life. Right now it's winter and it's really, really cold. When you guys go outside, you don't really want to be out there. It kind of slows everything down. But in the summer, when it's nice and warm, you guys want to be out and active, so you're moving a little bit faster. That's just like what happens in a sample. The higher your temperature, the higher your kinetic energy. So molecules in warm water are going to move significantly faster than molecules in cold water. So we can use temperature to help us have an understanding of, is my substance moving fast or is my substance moving slow? So temperature helps us understand how fast or slow our particles are moving. So let's look at an example. I have an insulated box right here, which basically just means no heat can get in and no heat can get out. So everything's trapped inside my box. I have a sample of hot water at 90 degrees Celsius next to a sample of cold water at 10 degrees Celsius, separated by a metal wall. Now the reason we have the metal wall is because we know that it will conduct heat. So it's going to allow these two samples to interact with each other. What's eventually going to happen is because my hot water has a higher kinetic energy than my cold water, its molecules are moving faster. And so they're going to go ahead and they're going to hit this metal wall more frequently than the cold water. And what's going to occur is some of the energy is going to get transferred from the hot water to the cold water. So eventually those two samples are going to reach the same temperature because they're going to eventually average out. They're going to equal each other eventually. So how you can calculate what that average temperature is going to be is you can take the temperature of your hot substance, add the temperature of your cold substance, and divide by 2. So if we look at this example, my hot substance is 90 degrees Celsius, my cold substance is 10 degrees Celsius, and I can divide that by 2. Now we know that 90 plus 10 is 100, so when I divide that by 2, my temperature would end at 50 degrees Celsius. So eventually what's going to occur is these two water boxes basically are going to even each other out at an average of 50 degrees Celsius. We call this phenomenon, the averaging of those two temperatures, the flow of heat. And this vocab word is really, really important because heat and energy kind of are interchangeable in this unit. So anytime I say the word energy, you also want to think of the word heat. How we show heat with its symbol is this little letter Q. So that little letter Q represents heat, so keep that in mind. And basically what heat is it's the flow of energy due to a temperature difference. And it can be any difference. It can be 1 degree or it can be 100 degrees. The temperature difference does not matter. You just have to have two samples that are at different temperatures. And how heat flows is it always goes from hot to cold. And now in chemistry, there's really no such thing as cold. It's basically just the absence of heat, but whatever. I just kind of care that you know heat always goes from your hot object to your cold object. So what's really happening is because this has a higher kinetic energy, it has more heat. And that heat will travel through the metal to the other side until these two temperatures eventually equal each other out. At that point, we don't have any more heat flow because we no longer have a temperature difference. So as long as one object is warmer than the other, the heat will always move from the hot to the cold until they reach the same temperature. That will always happen no matter what. So what we really want to do is we want to know which way is our heat moving. Is our heat moving, basically to the right, or is the heat moving to the left? And how we can do that is not by calculating the final temperature, but by looking at the temperature change. That temperature change is going to tell us who's gaining heat and who's losing heat. So this is the equation that we can use for temperature change. Remember that little triangle means that we're talking about a change in something. And so how you can calculate the temperature change is you can do the final temperature minus the initial temperature. So if I go back to this example, and I wanted to calculate the delta T for my hot water, my final temperature of my sample was 50 degrees Celsius, and it started at 90 degrees Celsius. So my temperature change would be a negative 40 degrees Celsius. And that's okay, because what this negative sign means is that my temperature dropped 40 degrees, meaning that I lost heat. So when your temperature goes down, it means that heat is leaving you and going someplace else, and that's fine. So that negative temperature change means heat was lost. We can do the same thing for our cold temperature. My delta T is going to be my final minus my initial. My final temperature again was 50 degrees Celsius, but this time my initial was only 10 degrees Celsius. So here my temperature change was a positive 40 degrees Celsius. And what that positive sign means is that my temperature increased 40 degrees. So that means that heat was gained. And that's super, super important that we can define whether heat's being gained or heat's being lost, because that is our sole focus in chemistry, is who's gaining heat or who's losing heat. So we can use temperature change to help us figure out who's losing and who's gaining. Now, one side note for you guys, because these masses of water were the same to start, these calculations are very, very simple. If we had different masses of water, these calculations would get much more complex. I would not give you something like that on the test. If I was asking you to either find the final temperature or asking you to find the temperature change in an example like this, I would only give you equal masses of water to start with. Otherwise, the calculations would be much, much, much more difficult. So, just a quick recap of what we learned so far. Kinetic energy is linked to temperature. The faster I'm moving, the higher the temperature. The slower I'm moving, the lower my temperature. That temperature helps me figure out who's going to gain heat and who's going to lose heat, and I can do that by calculating a temperature change. And this is our main focus in chemistry, is we want to look at who's gaining heat and who's losing heat. And so in order to do that, we have to look at two vocab words, because now that we know how heat's moving, we need to define where the heat's going. So who's losing and who's gaining. So as a chemist, when we look at the universe, we have two major parts. The first part is called our system. And what the system is it's the specific part of the universe that we are focusing on that we're focusing our attention on. And in chemistry, this is always going to be your reactants and products. So if we were doing a chemical reaction in this beaker, our system would be the reactants and products that we put inside. So that would be what we're focusing our attention on, because we want to know what's happening when we put those two things together in the chemical reaction. Everything else is going to become the surroundings. And by everything else, I mean absolutely everything else. So anything that is not the reactant or the product. So that would include things like your beaker. That would include things like your lab table that you're putting the beaker on. Your hands that you're touching the beaker with, the air in the room around your beaker, your teacher, the ceiling tiles, the gas that's in the hallway, the clouds in the sky, the grass on the ground. All of that's part of the surroundings. So the system is a very, very, very narrow and defined focus as the reactants and the products, where the surroundings is literally everything else. And it's really important that you kind of think about that. So even that beaker, it's just a containment vessel for the reactants and the products. It's part of the surroundings. So the surroundings literally includes everything else you can think of. And this is really important now, because what we can do is we can define whether heat is going into the system or whether heat is exiting the system. And that is our main focus as a chemist, is we want to know if energy or heat is leaving, or if energy or heat is being gained. So we want to know which way the energy and heat is flowing. So if you're putting energy into the system, your energy change is going to be greater than 0. So you're going to have a positive energy change. So I like to call this like a deposit. So when you make a deposit into your bank account, what you're doing is you're putting money in that's making the overall amount of money that you have increase. That's exactly what happens when energy goes into a system. When energy goes into a system, you're making a deposit that's making your overall energy higher. When energy is leaving a system, it's a negative energy change. And that's going to be like a withdrawal. When you take money out of your bank account, it makes your bank account get lower. That's the same thing that happens when energy is leaving the system. It's withdrawing energy from it, so it's going away. So energy in is going to be a positive energy change. It's going to make your energy higher, while energy out is going to be negative energy change, which is going to make your overall energy lower. And we can define those two changes with two very specific words. The first one is called exothermic. That word exo means exit. So when heat is given off by a process, it's called exothermic. So energy is flowing out of the system. The most basic example of an exothermic reaction is anytime you burn something. It will always feel hot. So you're going to be able to feel the heat from that process. The opposite is called endothermic. In an endothermic reaction, you're absorbing energy. So energy is going into the system. And this would be like boiling a pot of water. In order for us to get a pot of water to boil, we have to put energy into that water. It just won't do it on its own. So you're putting energy in. So energy is going into the system. So it's endothermic. I like to think of this as endothermic because energy is going into the system. Now, if you're just doing this in a test tube and all of a sudden it feels cold, that would be an example of an endothermic reaction because the heat is being removed from your hand into the test tube, which is how you get the cold sensation. And I'm going to talk a lot more about this tomorrow in the set of notes because we're going to go into a lot more detail into endothermic and exothermic tomorrow. So what we can do now is we can define whether something is endothermic or exothermic based on how the heat is flowing. So anytime heat leaves, heat's exiting, so it's exothermic. You're going to have a heat change that's going to be less than 0. So you'll see a negative change in energy or a negative change in your Q value, which remember again means your heat. So you'll have a negative value for an exothermic reaction. For an endothermic reaction, heat's going into your system. So your heat change will be greater than 0, meaning you'll have a positive change in energy or a positive change in heat. So endothermics are like deposits, while exothermics are like withdrawals. Tomorrow, we're really going to focus on what these words endo and exo mean in a lot more detail. So please take some time to fill out the Google form and put any questions you have into that form as well. Remember, if you have any questions, you can always swing by in the morning or shoot me an email. Have a great night, guys.